Neural networks are incredibly powerful tools for solving complex problems in machine learning, but training them effectively is crucial for optimal performance. In this lesson, we'll dive into the essential process of training neural networks using gradient descent, where our goal is to minimize the loss during the training phase. Today, we'll explore how feed-forward propagation and backpropagation work together. They refine our model iteratively to achieve minimal loss. So let's break it down step by step, starting with feed-forward propagation, which is essentially how our input data makes its way through the network. Imagine we're feeding data in, layer by layer, and this produces an output. Now, this output isn't perfect, right? And that's where backpropagation comes in. It's like the network's way of learning from its mistakes. By calculating the error and pushing that information back through the network, it helps adjust the weights to improve performance. So with each iteration, both feed-forward and backpropagation work hand in hand, enabling us to refine our model inch by inch. Remember, effective training requires patience and practice, so don't rush the process. In upcoming lessons, we'll delve deeper into these concepts, equipping you with the knowledge to train your neural network successfully. So far, we've learned about the key components involved in building a neural network, including the input layer, hidden layers, and the output layer. We also covered how to initialize weights and biases. We explored the processes of feed-forward propagation and backpropagation, focusing, of course, on the importance of weight updates and monitoring loss for effective training. Additionally, we implemented a training method that allows us to iteratively improve our model's performance using a synthetic dataset. Overall, these foundational elements are essential for developing and refining machine learning models. Now, let's explore gradient descent, the backbone of the training process for neural networks. So, simply put, gradient descent is an optimization algorithm used to minimize the loss function. It does this by iteratively adjusting weights in the opposite direction of the gradient of the loss function. Now, what do we mean by gradient? Well, the gradient tells us the direction in which the loss is increasing most steeply, and by moving in the opposite direction, we aim to decrease the loss. It's all about finding the most efficient path to improve our model's performance. Now, let's implement the mean squared error function, which is crucial for calculating our loss during training. This function takes two parameters, yTrue, which contains the actual labels from our dataset, and yPred, the predictions that our model outputs after a feed-forward pass. So what does this function actually do? Well, it computes the mean of the squared differences between these two sets of values, giving us a scalar loss value that indicates how well our model's predictions align with the true labels. By minimizing this loss, we can iteratively update our weights, which helps improve our model's performance during training. This straightforward definition captures the essence of loss calculation that drives the gradient descent process. Smaller loss values mean more accurate predictions. In essence, this function serves as the foundation for our gradient descent approach, enabling us to evaluate the accuracy of our model effectively and guiding our weight adjustments in the subsequent training steps. Thoughtful pause. Understanding and implementing this function equips us with a key tool for refining our neural network and achieving our optimization goals.
Now, let's take a look at how we can implement the backpropagation method within our neural network class. The first step in this process, super important by the way, is to compute the output errors. These errors represent the difference between the actual target values and the predictions we've made with our model. This calculation is crucial as it highlights just how far off our predictions are, which really guides us on where to adjust the model. Next up, we need to calculate the hidden layer errors derived from those output errors. This is done by performing a dot product with the transposed weights connecting the hidden layer to the output layer. And let me tell you, this step is essential. It informs us of how significant the output errors were on the hidden layer neurons, enabling effective error propagation. Once we have both error values sorted out, the next part of the code updates the weights using the gradients computed from these errors. We scale these gradients by the learning rate, which is key.
we're adjusting the weights between the hidden and output layers, as well as between the input and hidden layers. This application of gradients really reinforces our understanding of gradient descent, which, as you may know, minimizes loss by guiding weight updates in the direction that decreases error. So, this backpropagation method, it plays a pivotal role in refining our neural network's performance through those repeated learning cycles.
Now, let's take a look at a function designed to visualize the training loss over epochs, which is super important for assessing the model's learning process. This function is called plot loss, and it takes one parameter, loss history, which is a list of loss values collected during training. Inside this function, we're going to use matplotlib to create a plot that shows how the loss decreases over time, giving us a nice representation of each epoch. We start by plotting the loss history against epochs using a blue line, which gives us a clear visual of the model's performance throughout the training iterations. The title, Loss Reduction over Epochs, gives context to what we're looking at, and the x-axis, labeled epochs, helps us see the progression of training. On the y-axis, we have loss, which shows the magnitude of loss, helping us evaluate changes in model performance. By adding a grid to the plot, we make it easier to read, allowing us to pinpoint specific values with a glance. Finally, we call plt.show to render the plot, letting us visually assess how well the model is learning, whether it's reaching a stable low loss or oscillating wildly. This visualization is really key in determining optimal learning rates in fine-tuning our training process.
The displayed figure titled Effect of Learning Rates on Loss over Epochs illustrates the changes in loss values over 100 epochs for 3 different learning rates. Each learning rate is represented with a distinct marker and color: blue circles for learning rate 0.01, green squares for learning rate 0.1, and red X's for learning rate 0.5. If we take a closer look, all 3 curves trend downward overall, meaning that as the epochs increase, the loss decreases, which indicates that the model is learning in every case. However, there are some notable differences in speed and stability among them. The blue curve, representing a learning rate of 0.01, displays a gradual and relatively smooth exponential-like decay and loss, coupled with small point-to-point variance. This means we have slow but stable convergence here. Now, the green curve at 0.1 descends more quickly than the blue one, reaching those low loss values earlier with some modest fluctuations. This suggests a good balance between convergence speed and stability. But let's check out the red curve, which corresponds to a learning rate of 0.5. It drops steeply at first, indicating a very rapid initial reduction in loss. But it exhibits larger fluctuations and noisier behavior across epochs, sometimes oscillating rather than steadily decreasing. This pattern hints at instability and the risk of overshooting the minima. So, from these patterns, we conclude that a very small learning rate gives us stable but slow training, whereas a very large learning rate can deliver rapid initial improvements at the cost of unstable convergence. Meanwhile, that mid-range learning rate, like our example of 0.1, often strikes a practical balance between speed and stability for this setup. Lastly, the legend, axis labels, those include epochs and loss value, and the grid all help to clarify these comparative trends across the full range of 1 to 100 epochs.
Now, let's dive into implementing the training method for our neural network, allowing it to learn and adopt over multiple epochs. We'll kick things off by initializing an empty list called loss history. This is where we're going to track the loss at each training epoch, and it's super important for our analysis later on. As we work through the specified number of epochs, the network is going to generate predictions using the feedforward method. Now, at this point, we'll compute the error using the mean squared error function. This will help us understand how well our model's predictions are matching up with the true labels. Each time we calculate the loss, we'll append that value to our loss history, capturing the model's performance over time. This historical data, let me tell you, is going to be crucial for analyzing the training process. It also allows us to visualize the learning curve, which is really helpful. After calculating the loss, we'll call the backpropagation function. This is where the magic happens, adjusting the model's weights based on the gradients derived from that loss. To keep track of how we're doing, we'll provide feedback every 100 epochs. That's right, we'll log the current epoch along with the associated loss. This feedback loop not only helps us monitor progress, but also aids in fine-tuning the model's hyperparameters. Finally, once all the training is done, we'll return the loss history.
This step is essential because it allows us to visualize how the loss has evolved throughout training. So let's get into it. Now, let's implement dropout, a really useful technique that helps prevent overfitting by randomly disabling a fraction of neurons during the training process. In the dropout function, we first check if the specified dropout rate is less than 1. This indicates that yes, we want to apply dropout. If that's the case, we create a mask using a binomial distribution to randomly select which neurons will stay active. Each neuron has a probability of remaining active that's based on the dropout rate we provide. Following this, we multiply the layer's output by the mask, effectively setting the outputs of the dropped neurons to 0. But to maintain the scale of the output, we also divide by 1 minus the dropout rate. This scaling ensures that the expected sum of the outputs remains unchanged, allowing the model to generalize better during training. Now, if the dropout rate is set to 1 or greater, we simply return the original layer output with any modifications. This function, you see, not only enhances the robustness of our model, but also contributes significantly to improving its generalization to unseen data, making it a really valuable addition to our neural network training process.
As we wrap up our discussion on training neural networks with gradient descent, I want to emphasize just how crucial each concept we've explored today really is. Understanding how to propagate errors and adjust weights is fundamental for improving your model's performance. The iterative process of gradient descent allows us to refine our model, inching ever closer to that optimal state. With this strong foundation, you're now much better equipped to tackle more complex architectures and datasets. Sure, training neural networks can take time and patience, but by applying these principles, you're on a solid path to mastering this essential element of machine learning. Thank you for joining me in this exploration. Stay curious and keep experimenting.